Hello my dear students, today in this video I'm going to explain you about how to draw the shear force and bending moment diagram for a cantilever carrying a UDL and a point load. Now here you can see a cantilever capital AB which is fixed at B and free at point A. It is carrying a UDL of 5 kN per meter over the entire span of 4 meters, and there is a point load at the free end that is 10 kN. For this thing we need to calculate the shear force and bending moment and draw the shear force and bending moment diagrams. Now for this thing what I'm going to do here is just let us consider a section. I'm taking a section. Let the section be capital X and X. It is located exactly at a distance of small x from point A. Now with respect to this section we are going to generate the shear forces and bending moment and draw the SFD and BMD. Now shear force at any section X and X. Now I am considering right side of the section. According to the definition of shear force is nothing but algebraic sum of all the unbalanced vertical forces which are acting towards right or left side of the section. Now I am considering right side of the section. Towards right side of the section we have 5 kN acting over a span of x meter and 10 kN acting at a point capital A. 5 kN is acting over span x. Now according to the sign convention which I gave you, towards right side all the forces which are acting in the downward direction should be taken as positive and all the forces which are acting in the upward direction should be taken as negative. Now as these two forces are acting in the downward direction and they are on the right side of the section, let us take them as positive. The first force is 5 kN plus 5 kN multiplied by x. It is the load 5 kN acting over 1 meter. So we have x meters here, it will be 5 kN multiplied by x plus 10 kN. So shear force at any section X is equal to 5 times X plus 10. Now my intention is to calculate the shear force at point A and point B. Shear force at point A, that means shear force at X is equal to 0. So this will be equal to 5 times 0 plus 10, which is equal to 10 kN. Now shear force at point A, it is equal to 10 kN. Similarly, let us calculate shear force at point B. Shear force at point B, that is shear force at a distance of x is equal to 4 meter, will be 5 times 4 plus 10, which is equal to 30 kN. 5 times 4 is 20 plus 10 is 30 kN. Now shear force at point B, it is equal to 30 kN. So we got 2 points over here. First let us draw the shear force diagram, then we'll go with the bending moment diagram. To draw the shear force diagram, I'm just drawing some development lines here which are indicating the length of this particular beam. Next, draw the baseline. Above the baseline all the positive values should be indicated and below the baseline negative values. Now here we have point B and here we have point A. Exactly at point A shear force is 10 kN. I am marking 10 kN here. This is 10 kN. And exactly at point B we have 30 kN. I am marking 30 kN here. This is 30 kN. And what will be the variation from point A to point B? It will be linear. Why is it linear? Because we can see the shear force equation. We have x to the power 1 single degree equation. So the variation will be linear. Just draw a straight line joining point A to point B. So this will be positive and it is the shear force diagram which we get. Just decorating this thing. So we have shear force diagram here. This is the shear force diagram. Similarly, let us calculate the bending moment and draw the bending moment diagram. Now bending moment at any section X and X will be equal towards right side of the section. 5 kN is trying to bend the beam in the downward direction like this. It will try to bend the beam in the downward direction, and also 10 kN will also try to bend the beam in the downward direction. So 5 kN and 10 kN, when they are bending the beam in the downward direction, they are creating some hogging movement, then it will be negative. So minus 5 multiplied by x is the load, multiplied by x by 2 is the perpendicular distance. Load multiplied by perpendicular distance. 5 into x is the load, x by 2 is the perpendicular distance. And next 10 kN. 10 kN is the load multiplied by x is the perpendicular distance up to section x and x. So we have the bending moment equation, that is minus 5x square divided by 2 minus 10 times x. So here you can clearly see we have a quadratic equation to the power 2. Then the variation of bending moment curve, right, it will be parabolic. Now bending moment at point x is equal to 0. That means bending moment at point A. So this will be 0. When I substitute 0 in the here, we will get value of 0. Now similarly, bending moment at a distance of x is equal to 4 meter. That means bending moment at point B, we have minus 5 times 4 square divided by 2 minus 10 times 4. You will get the value as bending moment at point B, that is equal to minus 80. 20 multiplied by 5 divided by 2. 50 plus, okay, totally we will get 80 kilonewton. The units are kilonewton meter, and already we have bending moment at point A, that is equal to 0. We got two values here. Now using these two equations and two values, just I would like to draw the bending moment equation. The same thing again, we need to draw the baseline first. So this is the baseline, and with respect to the baseline at point B and at point A, I am going to mark the bending moment values, right? Bending moment at point A, it is equal to 0, and bending moment at point B, it is minus 80 kilonewton. Minus, negative means it should be drawn below the baseline. So just I am marking some point over here. Let us take this one as 80 kilonewton meter bending moment at point B. Now the variation in between these 2 points, it will be parabolic. Just I am writing parabola here, parabolic, and this is negative. Now this will be the bending moment equation, and bending moment curve diagram we obtain. That's it. Thank you.